All right. So I got my smart glasses on today because we're going to talk about some really smart computer sciencey sort of things. This is a topic that, if you're going into computer science, will be useful to you, and you want to know about it, and you want to be able to talk about it semi-intelligently. I say semi-intelligently because I think there are probably like a dozen people on the planet who can really talk about recursion in a truly intelligent way. It is sort of like the holy grail of computer science thinking in that it is very theoretical, and honestly, it's used for a very small set of problems. And when you can use it effectively, it's really kind of cool. But I will say up front that every single thing you can do with recursion can be done another way. There is no problem on the planet that absolutely requires recursion. So just sort of keep that in mind as we go through this. So recursion is sort of like these nesting dolls in that it it takes a problem and it sort of goes inside itself to solve tinier and tinier or more specific problems until you get to the smallest one, and then it goes back up very quickly to the largest problem and wraps it up. It sort of goes inside itself, and that'll make sense in just a minute. An example of recursion is a fractal image like this one, where you can see these patterns are repeating themselves at smaller and smaller scale. And in theory, these fractal patterns will go to an infinite level of detail, and that's kind of why they spiral. Typically, a fractal often looks like a spiral because any curve, you can see the curve in itself gets tighter and tighter. So that's just sort of, it's a very mathematical sort of concept. And you can even see fractals or recursion in nature. This is a type of broccoli, in fact, that grows like this with these patterns. I don't know what it tastes like. I don't think I want to eat it, but it's nice to look at. But you can see those repeating patterns, and even inside each little node or whatever, it has the same pattern as the big. So it's really kind of, I think, visually satisfying. And it's sort of visually satisfying in the same way that recursion is mentally satisfying for some of us. And essentially, recursion in computer science or programming is a function that calls itself. So that's kind of weird to begin with if you think about it. If I have a function like this countdown counter, so it'll take a number as int counter, and it will count down to 0, printing out each number in succession. And you can see it's defined countdown and taking int counter as a parameter. Then it prints the number, and then it says if int counter is greater than 0, then call the function countdown with int counter -1. So every time this countdown gets called, it'll get to here, and if it's still bigger than 0, it will pass this parameter back, which is that number -1, back to the function. So if we started at 10 with int counter, it would print 10. It would say, yes, it's bigger than 0. And then it would call that function again. It would call itself with 9. Let's take a look at that in a live code context so we can kind of see how that's happening here. Okay, so let's start with just the recursion. Okay, so what I have here is that same function, the countdown timer. Oh, you can always tell when I was doing some actual coding because my font size is set back to a non-grandma size font, which is, like what I want to use when I'm actually coding. What's going on here? There we go. Yeah. All right. So there we go. Now you can see that's the same code. And then what I have here is just gathering user input to get any number so we can try this out. And then it passes that number to the countdown function as a start. So this is going to run until this is no longer true, because then it will stop calling itself. Okay, so let's run this. What number should I count down from? Let's try 10. Okay, and as expected, it counts down from 10. Now, recursion is absolutely not necessary for us to do this successfully. It's kind of just a flex, if you will, because it's actually less code to do this in an iterative way. So I've got another one called count easy that takes the same int counter, and basically it just says for int x in range, whatever that number is, to -1. It's -1 because if I stop at 0, then it won't include 0. So I got to go 1 past 0, and I'm counting backwards. Oops, what did I just do? Oh, there we go. It's counting backwards by ones. So print int x each time it counts down. So if I try both of these sort of side by side or one after the other, I have 5. You can see they both produce the exact same output. Recursion is not necessary here, but it's a very basic example of what it means to call a function inside a function. So looking at something that is better for recursion, let's say we have a nested list like this, where we have lists inside of lists inside of lists. Okay, you can see I color-coded these to make it a little easier, and I also use names. These are a list of names or objects that start with each letter is a different list. So all of the A words are the top level list, the B words are level 2, and the C words are the third level down. And if I peel that apart, you can see that the first list contains Adam, Alex, and Ann, but it also contains 2 sublists. Okay, the first sublist is found in index number 1. Then it contains Bob, Barb, and Bert, and then it contains a sublist there of Chet and Kat, and then back at the first list in index number 0, 1, 2, 3, 4, 1, 2, 3. So index 3 here contains B and Bill. Okay, so a nested list is one of the best applications of recursion. Going through a nested list and printing each value or counting the value or doing something to each value in a nested list, or what may also be commonly known as a tree structure, is one of the best ways to use recursion. Recursion can also be used for sorting algorithms. Anytime you are doing something that's repetitive, where you're doing something that's repetitive on a increasingly detailed level, so something inside of something else, or you're branching out, recursion is a great way to handle it. It's never the only way to handle it. I can't stress that enough. You never have to use recursion. There is no problem that requires recursion. But this one in particular is way easier and way more elegant if we do use recursion. So let's look at this list of names. So if I'm traversing this nested list, I would start with Adam. And then the way we do this with recursion is a little bit different, because in our mind, what we might want to do, what we might be inclined to do, is if we were going to count the number of names in all of these lists, what we might be inclined to do is count all of the A names first, and then all of the B names first, and then all of the C names. That's just sort of how our brain works. But when we're traversing a tree structure or a nested list using recursion, it does something interesting. So it would start with Adam, because that's the first list, index 0. But when it reaches index 1, it encounters another list. So what it does there is it follows that link into the sublist. So it will grab this first B list and it will start at slot 0 there. Then it will traverse to the B list slot 1 or index 1. It encounters another list there. So every time it encounters a sublist, it's going to follow that link down. Then it will complete that sublist before returning to the B list in index 2. And then when it completes that list, it returns to the next element of the first list. And then the index 3 of the first list, or the primary list, is another sublist that contains B names. So it's going to follow that, complete that list, and then finally return to the final element in the top list. And the reason that it does that is because each time it encounters something, if it encounters a name, we're going to count that name or print that name. If it encounters something that's not a name, but it's a list, then that's where the function calls itself and uses and passes this list as a parameter. Then it does the same thing, prints the name, and then it counters another list. So it passes that list as a parameter, finishes that list. And then once it's done here, because this is running inside, it's a function inside a function. So when this function completes, it goes back to this function and completes that one before going back to the main function. So that is how recursion works, or how it looks. So the logic here is, if I'm doing it in sort of pseudocode, for each item in that list, if it's a single item, we print it or count it. Otherwise, we process it like a list, which means we call that function again. So let's take a look at the code for that. Okay, let's get rid of that so we can see what we're doing. Here is the exact same list that we've got with the branches. And I've got a function here called count leaf items. And it takes a list as a parameter. So first thing it does is it prints the list. And then it prints, or it counts, sets a count to 0. This is really interesting to me, at least, to wrap my mind around, because every time this function gets called, it sets the count to 0. But yet we're counting the number of names. So the way this works is going to be very interesting, and I'll show you in just a minute when this runs, because what it does is it actually prints the count down here. Each time it counts something, it'll print the count. But the count is going to do some weird things, because every time we go to a sublist, it starts back at 0. But we still end up with the right answer at the end. So for item in sublist, or so for each item in the list, and basically this just says if it's a list, then we print that we encountered a sublist, and here's the recursion right here. Except, look at what we're doing. We're adding to count. We're adding to the count whatever's returned when we call that sub function. So we call that function and we add it to the count. So that's where it gets totaled at the very bottom. If it's not a list, Then we count the item, right? And we print out what we counted. And then after all of that, we return the count, and we say we're returning the count. So all I'm going to do here is call that function. Okay, if we're not including the function, we've got 3 lines of code here. We've got the list, the function, and the calling the function using the list. So that's where it starts. So when we run this, we're going to get some really interesting stuff happening. Okay, and it works just like we talked about. The first thing it does is it counts Adam. It returns a count of 1. It says we encountered a sublist. The sublist is the B names and the C names as a sublist that's in index 1. So we're counting the leaf item Bob, which is the first item there, and then we say, count is 1. Count is still 1, but we've actually counted 2 names now, Adam and Bob. But this is just the count inside that function at that point. And then we encounter another sublist with Chet and Cat. So we count items Chet and Cat, 1 and 2. Now that's making more sense. And we return. Okay, so this is the first time the return gets sent back to the previous. So we're sending 2 back because that C list had 2 in it. Then we count Barb and Bert, which are the final 2 names in that first B list. Let's keep that list up here. So we counted all of these through Barb and Bert. And then we're returning 5. The 5 that we're returning are Bob, Chet, Cat, Barb, and Bert. Because we've already counted Adam, but that was in a previous instance of that function. So now, when we count Alex, the count is 7. Because we counted Adam, we sent back 5, and now we counted Alex. So the count is back up to 7. Then we encounter another sublist. Count gets set back to 0, and we count B and Bill for 2. We return those 2, and then we count N, which gives us a grand total of 10. So that's how it follows that tree structure through, and it's a great way to look at how that tree structure works. Tree structures are very, very common. Okay, that you would think, why would you want a list inside a list inside a list? Well, a tree structure is very common, and in fact, one of our other previous assignments already uses a tree structure, and that's this one. Many of you did not attempt this one, but this one actually has a tree structure. When we're looking at websites, they have a tree structure. When we're looking at outlines, they have a tree structure. So this kind of tree structure is very, very common out there in the real world. And when we design a program that tries to make sense of one of these naturally occurring tree structures, recursion is a great way, a very powerful way to explore that code without knowing how deep that tree structure goes, because recursion is just going to keep looking for more branches inside of each branch. And that's the nice thing. If I tried to solve this in an iterative way, I would have to keep adding to my code or put in some kind of mechanism that says, okay, when you stop finding branches, just stop counting. You could do that, but recursion is really cool because it acts like an automated explorer that kind of just goes through the structure and tries to figure it out. So when we're talking about things like artificial intelligence, about algorithms that try and make sense of any sort of naturally occurring phenomenon, human behavior, or language, or construction, or the way animals behave, all of those things can be best understood using a recursive algorithm. So that sort of recursion is becoming more and more important to the kinds of programs that we're writing for understanding our real world. And Python is maybe surprisingly one of the primary tools that we're using to analyze that kind of data. It's very, very common to see Python used as a primary tool in training AI engines because it has this level of power and just ease of use. So while you don't have to solve anything using recursion, it's really good to know about it, to kind of know how it works and to have an idea of how it's implemented, especially if you're going into computer science, because one of the fastest growing areas of computer science is artificial intelligence and machine learning. Both of those use recursion in a very powerful way. So anyway, there is no assignment for this module. If you want to try recursion out, I would encourage you to try it out with the web crawler. Both the crawling and the printing of the sitemap can be done using recursion. And you can see in my code here, I'm using recursion to print the map. So I'm having it traverse that tree using recursion. I didn't have to, but I wanted to play around. You can also use recursion for crawling a website anytime you're looking for trees and branches. So if you want to play around or challenge yourself with recursion, that's a great project to work on. Of course, you can also play around with the trees, the list and branches. And I'm gonna upload this basic recursion code and the recursion counter code to Canvas so that you can play around with them. But like I said, there is no assignment that requires recursion, and this is more of an FYI, a more important FYI if you're studying computer science.